All right. Hey, everyone. So, excuse me. Today I'm going to go over the notes for 4 oxidation reduction reactions. Okay. Oxidation reduction reactions are actually a pretty big category of reactions within chemistry. So, when we were starting out in Chem 1, um, we classified a lot of the simple reactions, like the single replacement, double replacement, decomposition, synthesis, stuff like that. Um, when you get into chemistry a little more, like you guys are in Chem 2, and then obviously further along, if you were to go on in college or stuff like that, um, a lot of times they actually change and they categorize not sort of by like the style of the compounds that react, but like specific things like combustion. They'll categorize them more like that. Oxidation reduction sort of falls into that category. It's a generic category, but it's um, it's more based on what is happening in the reactions um, than a specific sort of model of the cation, anion, stuff like that. Okay. Um, so oxidation reduction, you'll see it a lot of times, they'll shorten it to redox reaction, involves the transfer of electrons between reactants. Okay, so you've got, and you can see I've already marked this from before, so I'll kind of explain through it. But um, when a substance loses electrons, it undergoes oxidation. When a substance gains electrons, it undergoes reduction. So we know from general chemistry that uh, we have when things bond, they either give up, accept, or share electrons. That's how a reaction occurs. Is the transferring of electrons or the sharing of electrons. Okay, so a redox reaction categorizes this in terms of actually gaining or losing. All right, so they have the equation here, and I just literally rewrote the equation over here so I could do this with it. Um, if you look, you've got solid calcium combining with a hydrogen ion, okay, and you get calcium ion and hydrogen gas. Okay, so this would be like a net ionic equation. There might have been other stuff in there, but this is the real reaction part. So if you look, calcium from the left side, the reactant side, to the product side, calcium lost 2 electrons because it went from a 0 to a 2 plus. Okay, hydrogen gained 2 electrons. It one hydrogen. So if it goes from a +1 to a 0, that'd be gaining 1 electron, but there were 2 hydrogens that did that, so it gained 2 electrons. Okay. Um, so one of the ways you can remember this is the acronym OIL rig. OIL rig stands for oxidation is losing, reduction is gaining. This is about electrons. So oxidation is losing electrons, reduction is where something gains electrons. Okay. When you're looking at the actual substance, you can think of it as oil rig, or if you concentrate on the charges, um, I sorry, I'm laughing because it's kind of dumb, but I came up with this, which is like RLOG, like real life OG. Um, so if you're looking at the charge, not like the electron gain or loss, its reduction is losing charge, oxidation is gaining because electrons are negatively charged. So the charge essentially does the opposite of what the electrons are doing. So if you are losing electrons, you're getting a positive charge. If you're gaining electrons, you're getting a negative charge, or you're losing charge. So if you're looking at the charges from reactants to products, you would say reduction is losing charge, and oxidation is gaining charge. Okay, you can look at it either way. Just know which is which when you're doing that. All right. So so in this one here is a similar thing, except they're not showing it to you. So like here, um, if it's a single element and there's no charge on it, then it's neutral. It's 0. Okay, so if you look over here, you'd be like, well, there's no charges. But remember, this is a compound. So if you ionize this compound, calcium is a 2 plus, oxygen is a 2 minus. So that means calcium, from the reactant side to the product side, calcium actually lost 2 electrons, oxygen actually gained 2 electrons. So calcium was oxidized and oxygen was reduced. Okay. In redox reactions, you have to have something that's oxidized and something that's reduced. You cannot have one without the other. So if something got oxidized, there's something in there that had to be reduced. If there's not, you did the equation wrong or something. You're not seeing something. Okay. All right. So oxidation numbers. Oxidation numbers, or also called oxidation states, help us keep track of electrons during chemical reactions. Generically, we think of oxidation numbers or oxidation states as charges. Okay. If you're getting into very technical chemical terms, there is a difference, but that's not a level that we're going to go to. Okay. One thing to show you, as we're talking about this, on the periodic table that I gave you guys, right? And I've kind of showed this before, but the periodic table that I gave you guys, down here it shows oxidation state. So you will find the oxidation state, or we talked about it as being the charge, of the atoms down here on your periodic table. Okay. And some of them have more than one oxidation state. The most common one is bolded. All right. All right. So how do we know what the oxidation number is for an atom? Okay. There's some rules to help us do that. And I have highlighted the rules here in green. And you just have to memorize them. There's no other way. Okay. Excuse me. For an atom in its elemental form, the oxidation number is always 0. So what does elemental form mean? Well, elemental form essentially just means the element by itself, however that's normally found. So if it were, if it were potassium, it would just be K. Okay, now the ones that you have to realize are that some things, some atoms are like the diatomics, right? Your Hofbrinkel. So O2 or Cl2, that the oxidation number for those are 0. Okay. For any monatomic ion, the oxidation number equals the charge on the ion, positive for metals, negative for nonmetals. So those are all the charges that that we've used ever since way back in Chem 1, with our periodic tables, right? So +1, +2, +3, some of the charges in here. So for a monatomic ion, the oxidation number equals the charge on the ion. Okay. The oxidation number of oxygen is usually -2. The major exception is in peroxides, which contain the O2 -2 ion. Okay, so like something you're probably familiar with, hydrogen peroxide, right? The stuff we put on cuts is H2O2. If you ever noticed, I don't know if anybody ever noticed that, but it's not reduced. Okay. the O2 ion, this is a specific ion, it's O2 -2. Okay, in that case, an individual oxygen would be -1 because there's two oxygens at a total of -2. Okay, but oxygen is usually -2, which we already kind of knew from the periodic table, right? Oxidation number of hydrogen, now this one is a little different. We've always treated hydrogen for everything we've done really as +1. Okay, hydrogen is a +1 when it's bonded to non-metals. It's a -1 when bonded to metals. So you can actually bond hydrogen to metals, and it would act as a -1 then. All right. The oxidation number of fluorine is -1 in all compounds. The other halogens have an oxidation number of -1 in most binary compounds. So a binary compound is where it's two elements, one of them being a halogen. So that's this column, right? The halogens. Fluorine, always a -1. The other ones are typically a -1. If you were to look on your periodic table, you would see, sorry here, that fluorine only has a -1. Chlorine, bromine, iodine, these have other oxidation states, but the most common is the -1. It's almost always -1. Okay? All right. So those rules, most of that we already kind of knew. It's just working from those. All right. So then I've highlighted here some other rules. These aren't about the charges as much as they are about how you do this. So the sum of the oxidation numbers of all atoms in a neutral compound is 0. There's no charge on a compound, right? So the sum is 0. The sum of the oxidation numbers in a polyatomic ion equals the charge of the ion. Okay, so I'll show you that in a second here. So in general, if you want to sort of break it down into an equation form of how you can calculate the oxidation numbers and the charges and stuff, is you would take, this is for a compound, you take the atoms of the first element in the compound, the number of atoms, times the oxidation number of the first element. Add this to the number of atoms of the next element in the compound, and multiply that times the oxidation number of that element. And then you would keep going with however many elements there are. This has to equal the overall charge. If it's a neutral compound, the overall charge is 0. If it's an ion, polyatomic ion, the overall charge is whatever the charge is on the ion. Okay. All right. I'm going to walk you guys through some examples of these to show you how it works. So let's see here. This is a sample exercise from your book. It is page 138, sample exercise 4.8. Okay. You don't actually need to go to your book to see it. I've written what the instructions say, or what the problem says in the book. Determine the oxidation number of sulfur in each of the following. Okay, so we have here, excuse me, this. Now, we are going to do this number of atoms of element 1 times the oxidation number of element 1, like that kind of idea, okay? So what we're trying to find out sulfur, right? So if we look, we're going to take the number of atoms of hydrogen times the oxidation number for hydrogen plus, sorry, let me move this up a little bit here, plus the number of atoms of sulfur times the oxidation number for sulfur, and this is going to equal the overall charge. Okay. So, number of atoms of hydrogen, 2. The oxidation number of hydrogen. So this is where we go to our rules. Okay. Hydrogen is +1 when bonded with nonmetals. Sulfur is a nonmetal. So this is a +1. Okay. All right. Plus the number of atoms of sulfur, 1. The oxidation number of sulfur. We don't know that. That's what we're looking for. The oxidation number. So I'm going to put, you can put an X if you want. I'm going to put an S for sulfur, just a variable. Okay. Equals the overall charge. There's no charge on that, right? It's a neutral compound, so 0. And then we just solve for S. Okay, so we get S equals, this would be +2, take it to the other side, so S equals -2. This is the oxidation number for sulfur. So it's not really hard once you get the idea down. It's memorizing and remembering the rules and then applying them. Okay. So I'm gonna knock these other ones out here. So B, S8. Okay, now people get all freaked out because they're like, oh, there's 8. Like, what is it? Okay, it doesn't matter. Think of it this way. Okay, so this is elemental form. It's just a single element. There's no charge. So this is just sulfur is 0. Okay. If you want to see this as the equation, we can write it out. It would be the number of atoms of sulfur, so 8, times the oxidation number of sulfur, which is what we don't know, equals the total charge, 0. What times 8 equals 0? Well, sulfur equals 0, right? Okay. So we have the third one, SCl2. Okay, same type of idea. Number of atoms of sulfur, there's 1. We don't know the charge, that's what we're looking for. Plus, there are 2 of the chlorine. And okay, 2 of the chlorine. And we know chlorine. Okay, so chlorine's a halogen, right? Halogens normally -1. So we're going to put -1 and equals 0. All right, so we get S -2 equals 0, S equals +2. So here, in this case, sulfur is actually acting as a +2. All right. Na2SO3, same type of deal. 2 sodiums. Sodium is a +1. Okay, let me move this up a little here. Plus 1, looking for sulfur, plus 3, and our oxygens are -2. Okay, and that equals 0 because there's no charge. So solving this, we get 2 plus S -6 equals 0. So S equals a +4. Okay. All right, and the last one, E. So SO4 to negative, 1S, don't know the charge, plus 4 of the oxygen. Oxygen is -2. This has to equal -2. Equal the charge. It's a polyatomic ion, right? So we have S minus 8 equals -2. S equals plus 6. Okay. And by the way, when you're doing these, even though we're doing them kind of like a algebra problem, you do need to put the plus if it's positive. Okay. You don't. You can. I don't want just S equals 6. I want you have to because it's the oxidation number. The oxidation numbers have the pluses and the minuses on it. Okay. All right. So I'm going to go on and do a few more practice exercises. There's practice exercise from the same page underneath it. If you feel like you know what you're doing, you can either go to the homework, or if you think you know what you're doing and you want to practice a few, what I suggest doing is going to these and trying it, yourself on scratch paper or something, or pausing the video, and then once you think you have it, check and see with what I put down. Okay. So in this one, what is the oxidation state of the red colored element in each of the following? Okay, in your book it says bolded, but I don't have a way to do bold on here, so we're doing red. So A is P2O5. Okay, if you want to try it yourself, pause the video. Otherwise, here we go. Okay, so we have 2 of the P's, right? I'm just going to do it in red. So we've got 2, and we're looking for the P, plus 5. Oxygen is -2. No charge, so 0. So we end up with, let's see, 2P minus 10 equals 0. 2P equals 10. P equals +5. Oxidation number of phosphorus is +5. Okay. All right. Next one. NaH, excuse me. Again, pause it if you want, but here we go. This one, I'm not even going to write out all the equation. It's super simple. It's 0. That means they have to balance. Sodium is a +1 from the periodic table, which means hydrogen has to be acting as a -1. Okay. All right. C, Cr2O7, -2. Again, pause it if you want to try it. Here we go. So we've got 2 of the chromium. We have 7 of the oxygen equals -2. So chromium is a +6. Okay. All right. Sn in the SnBr4. So we've got oops. Sorry, I almost wrote Br there. Okay. Apparently we're erasing all that. So plus So Br, halogen, -1 equals 0. So SN10 is a +4. All right, last one. BaO2. So we got 1. So we're looking for the oxygen in this one, right? So Ba, if we look here, Ba is a +2. Plus, we've got 2, and we don't know the oxygen. That's what we're looking for. And this has to equal 0. Put a line through my 0, that way I can tell it from my O. All right, so we've got 2 plus 2O, 0. So oxygen, in this case, has an oxidation number of -1. All right, that's it for this. I hope it helped. I'm going to split this into these notes into two video sections, so you guys can kind of hop from one to the other. All right. If you have questions, as usual, let me know. Either come to the help sessions or message me on your own. Okay. Good luck.